Hi everyone, welcome back to my channel. So in this video, I'm going to show you me trying to use Gibbs sampling for building a dynamic linear model. A dynamic linear model is a model that's based on Bayesian framework. And so it's using Bayesian framework. So we have prior and posterior, and we have to set the variances. In real life, we don't know those variances. So we have at least two methods to approximate the variance. The first is using maximum likelihood estimation. I did a video about it in my second video. And then the second way or the second method is by using Gibbs sampling, which is the focus of this project. Let's study together. This project is actually a continuation from my very first project, my very first video, which I'm going to call the CodeTLM project. Okay, so the data I'm going to use is going to be the exact same data. I have provided the data on my GitHub, and this is the link. This is the link to my data. So yeah, in this cell, I'm just loading the data and then changing the class or the type of the date column and then sort the df so that the output df here is in an ascending order. These two lines here, I'm saving the high prices of gold as y high and the low prices as y low. We're talking about a daily time series that spans over a year. Okay, and this is the time plot. The high prices is in blue or the upper line, whereas the low prices is in orange or the lower line. Okay, now let's refresh our memory a bit about dynamic linear model. As I mentioned earlier, it's based on Bayesian statistics. And dynamic linear model sees a time series in hierarchies. The first hierarchy is the outer one, which is the observational level. All the values that we see on this time plot are on the observational level. But dynamic linear model believes that to get the values that we see now, it is driven by the level or the mean that is in the system level. So this system will give us the mean at each time point, and then if we add some variance to it or some white noise to it, we will get the value that we see. Oh, by the way, this data set starts from June 27, 2022 and ended on June 22, 2023, which is Friday. So we're going to forecast as well. We will do a little bit of forecasting, and yeah, the forecasted day would be the price for June 26. Okay, now another thing about dynamic linear model is that we can build a dynamic linear model for each component of the time series. So for example, if our time series has the trend and a seasonal component, we can build the model for each component and then concatenate them, or in the TLM literatures, it's called superposition. The final model would be bigger and more complete. Now, in my CodeTLM project, I used two components. They are the second order polynomial trend and the form-free seasonal component. Yeah, first of all, I want to say that I don't think the form-free seasonal component is necessary now that I think of it. It's just about the implementation of the cyclical pattern that we see in this time series that, yeah, maybe form-free seasonal model won't be the best. Now that I've been working more with this data, I've found a better model that's at least as good as the model that I did in my CodeTLM project. and that is the third order polynomial trend. Okay, before we get to know more about the polynomial trend dynamic linear model, I just want to show you these subplots. The subplots are the autocorrelation function and partial autocorrelation functions for both time series. And from these subplots, we can conclude that the gold prices are non-stationary, which is very common in financial time series, which is why I used dynamic linear model in the first place, because it doesn't need a stationary time series. We can just put into the model and filter it. Filter is like training it. Okay, so let's talk about polynomial trends now. Actually, a dynamic linear model is always described in at least two equations. Okay, one for the observational level and the other for the system level. But to make it easier, I think we should start from the observational level. So for the polynomial trends, whether it's the first, second, or the third order model, the observational level equation is the same, which is why at time t, I just omit the index t by the way to simplify it. So y is the value that we see, and then it's defined as the level plus some white noise. The difference between the first, second, and the third polynomial trend dynamic linear model is in how we define the level. Okay, I'm going to show you that more formally later in the R, but to get some intuitions about it, the third order model is for time series which looks like a quadratic equations. So, like, imagine that this is our curve and it's a function of the time. So to get the level at time t, let's say at this time point, we can just take the t and then project it to our quadratic equation to get the mean, and that's the mean. But to get the observed value, we have to add some white noise. Okay, so that's the idea of the polynomial trend third order dynamic linear model. Now let's look at how it is defined, especially how we define the level for the third order more formally. Okay, so these equations are how we define the third degree trend component. Actually, there are two representations of dynamic linear model. The first is through mathematical equations like this, and the second is by using matrix representation. I'm going to use the mathematical equations for now. So the first equation here is the one that we see in the slide earlier. It's the observational equations. It says that yt, which is the value that we observe, is defined to be the level mu plus some variance nu. And then the level mu at time t is defined to be the previous level plus some growth beta, and plus some variance or white noise around that level. I'm going to denote that white noise or variance as omega for mu t. Okay, and then furthermore, we can define the growth beta as the previous beta plus some growth of the growth. It's like acceleration, which I denote as gamma. And then plus some variance again. The variance is around the beta, the growth. Okay, then finally, the gamma at time t is defined as the previous gamma plus some omega, or the variance around the gamma. All these variances, nu and the omegas, are assumed to be normally distributed. Now, the nu is commonly called the observational variance, while the omegas are the system variance. Now let's look at this. Nu is normally distributed with mean 0 and variance v, while the omega, notice that I printed bold here, it's an array which collects all the omegas with for mu, for beta, and for gamma. They're also normally distributed with mean 0 and with their respective respective variance w. These variances are assumed to be independent, so each omega and nu has their own variance values. And in building the dynamic linear model, we have to set these values. Of course, by default, the function to implement this will have some values that are already set by default. But if we want to make a better model, we should choose a good value for these variances. In the GoldLM project, I just set it some values after trial and error process. But now I want to try another way, that is using Gibbs sampling. So what we're going to do is we're going to use Gibbs sampling to get the approximates of the variances, and then use these variances to build the dynamic linear model, and then filter it and use it for forecasting. Now in Gibbs sampling, we need some prior prior beliefs about what the values of these variances are. The conjugate prior for the variances is inverse gamma. So we're going to think of these variances as in inverse gamma distribution. Okay, now let's see how Gibbs sampling works. Okay, so this is how Gibbs sampling works, given that we already have the prior that we discussed earlier. So in Gibbs sampling, there are a number of iterations, and in each iteration, we take turns sampling for updating the parameter. So now in our case, we have 4 unknown parameters, right? And so let's say that the order is just like this. V is the first parameter to be sampled, and then omega for mu, and then omega for beta, and omega for gamma. We have the prior for these parameters, so we can index it as 0. So omega mu 0, omega beta 0, omega gamma 0, and v 0. Okay, now this is our first iteration, and v is in the first turn. So we want to sample to get v1, given the other parameters. Right now, we don't know anything about these parameters other than their priors. So v1 would be sampled conditioned on omega mu 0, and then omega beta 0, and omega gamma 0. We will also need the full conditionals, but we're going to get to that later. Okay, now let's say that v1 is already sampled, and we update the v1 or get the posterior for the v1. Now we take turns, and let's say now we want to sample for omega mu 1. Now the sampling process would be based on v1 and then omega beta 0 and omega gamma 0. We're not going to use the prior of v anymore because the v has been updated. Okay, so the posterior of v in this process now becomes the prior of the next sampling process. So in general, the conditionals for the samplings are based on the state of the parameters when the sampling process happened. Okay, so if we sample the omega beta at iteration 1, it will be conditioned on v1 and then omega mu1 because we have done the sampling, and omega gamma 0 because we still haven't sampled any values for omega gamma. So lastly, as the last parameter in this iteration, omega gamma 1 would be sampled based on v1 and then omega mu1 and omega beta 1. And it keeps going on like that. Now, some of you might be familiar with some other sampling algorithms like Metropolis Hastings. They are really similar, except that Gibbs sampling can sample more than one variables or parameters. That's why with 4 parameters like our project here, we have to use Gibbs sampling. At least this is one of the ways that we can implement to sample more than one parameters. Now, one thing we need to discuss is the full conditional distributions. This is needed for sampling the parameters. So like when we sample the v1, omega mu1, what are the distributions? So the prior is inverse gamma with parameters shape alpha and rate phi. But in the full conditional distributions, which is based on the posterior distribution, this is how we define the full conditional distributions, which is after the update, the shape would be like this, alpha plus n over 2. And then the rate would be phi plus the errors, the sum of squared errors divided by 2. And the rate, which is denoted in phi, is the reciprocal of the scale. Okay, so now to implement Gibbs sampling, we need to first initialize the model object. And as we have discussed before, we only want to use the trend polynomial component. So to initialize the object, we only need one function. So first of all, I'm going to name that object as model H because right now we're dealing with the high prices first. Okay, now what function do we need to build that object? Since we have agreed to use the model, the polynomial component only, that function would be DLM mod poly. Okay, and there are several parameters here. The first is the order. We have discussed before that we want to use the third degree of polynomial trend component, so the order would be 3. And then for dv and dw, that's what we're going to sample later, so I'll just leave it like that. And then to make it more similar to the DLM Code project, I also want to set the prior mean for the mean levels. So that's the M0. And we need to set it for 3 values. So you see, we have the third degree, so 3 variables, the mean, the growth, and the growth of the growth. Now, after initializing the object, then we put the model or the model object into the Gibbs sampler. Okay, and that Gibbs sampler, I'm going to name it as Gibbs, by the way. Okay, so the function to run the Gibbs sampler is DLM Gibbs dig. Okay, there are some parameters here, and I've shown you a little part of the documentation in this this block here. Okay, so for this one, first we need to pass the time series. Okay, that's gonna be the y high, and then the model, which is model h, and then the parameters for the inverse gamma distribution. In this function, there are two types of description, either by theta and beta. Either by A and B or by shape and rate. Usually when we study inverse gamma distribution, the two types of description is either by shape rate or by shape and scale. So I think the shape and the rate parameters would be more intuitive to us. So shape for the y, that means the observational level, and the rate for the observational level. The parameter shape is called like that because if we change the value for shape, we can see the effect immediately on the visualization of the distribution, on the shape of it. So that's why it's called shape. And I'm going to set it to 10. Okay, and then for the rate, I'm going to set it to 100. Okay, and then after setting the shape and the rate for y, we have to set the shape and the rate for theta, or the system values. I'm going to set it the same as in shape y and rate y. 100. Okay, and then a few more parameters. They are ensample and safe states. So ensample specifies how many iterations we want our Gibbs sampling to work. I'm going to set it to 3000. And then for safe states is the parameter to indicate whether we want to save the states, which is the theta values. Okay, we're going to train this model again anyway, so I'm not going to save the states. Oh yeah, this is not rate y but rate theta, sorry. Okay, alright, so now let's run this cell. So we can see that the sampling process is done now. And what is the output? What is the output of DLM Gibbs DIG? Gibbs, if you see here, Gibbs is a list of two elements. Okay, so if we look at this documentation, the function of DLM Gibbs DIG returns three values. 3 if we want to save the states, but we have set the save states to be false, so we only get 2, which are dv and dw. We can check the length of the vector dv and dw. So yes, this is a vector, not a single value, and I'll show you why. Alright, so we have 3000 iterations, right? So the dv and dw would be of length 3000. Actually, for dw, it will be a matrix, 3000 rows for each iteration, and the columns represent the variances in the system level. Okay, so why we don't have only one value? Because again, each sampling at each iteration, the Gibbs sampling will get a new posterior value. So this function stores all of those posterior values. That's why we get the ensample values. Okay, now I will run this cell, and this cell will shows us the plot of the dv and v and the w values. Okay, w1 means it's the omega or the system variance for the mean level. It's here, omega for mu, and then w2 is omega for beta, and the last one is for omega gamma. Alright, we can see that in these three graphs we have like this is called the burning period. So in this period, usually the Gibbs sampling, not only Gibbs sampling but all samplers, especially in MCMC, these samplers try various values, and usually we cannot see this sampler as a stable process. So like we need to warm up the sampler. That's why it's called the burning period. So after the burning period is over, the sampler can get to a stable value, if you will. Alright, so to get the posterior values, the final or the summary of these vectors, we can do it in the next cell, which is here. So I'm going to use the function MCMC min. Okay, so this is basically just taking the average of those 3000 values. Okay, and then MCMC min takes a data frame or a matrix. So that's why I have to do the cPoint function. cPoint is to concatenate the columns. Okay, and then the first column would be the dv, and then the next columns would be for the w or the system variance. I'm going to set the burning period to be 100. So this means that I don't want the first 100 values of both the v and the w. Even though, I don't know, maybe we can set it to a bit more than that, like maybe around 200. Yeah, let's just set it for 100 for now. Okay, I'll leave that to you to experiment on that burning period value. Okay, now let's look at the posteriors, and this is what we get. So after being sampled by the Gibbs sampler, we get that v is 12.3, and then the variances, w1 is 165, and then 10 and 4.9, almost 5. The bottom row is the standard deviation of those estimations. And now let's see how to use these sampled values. Alright, so after getting the sampled or approximated variances, we can get back to model H. So we reinitialize the model H. We call the TLM mod poly function again. And then for the order and the M0, we set it the same. But now we can change the default value for dv to be this value, which is the first row and the first column of posteriors. And then for dw, we just put all of these into one place. Now after reinitialize the object, now we can do just like the normal way of doing TLM, training TLM for this from this package. So we run the TLM filter, and then we put in the time series that we want to train and the model. The model, of course, has the sampled variances now. Okay, now for the rest of the codes, I calculated the squared error. The root mean squared error. So we will see the root mean squared error as the title of this graph. Okay, so this plot is the continuation from the very first plot when we plot both the high and the low prices. But now I'm just going to show the high prices and the filtered level. Okay, so this is the fitted model. And we can see that it looks really well. The RMS is only 0.64. A little caveat though. Well, I mean, this particular model, the DLM mod Poly with order 3, only works for this period of data. Like, you need to keep checking with your data and see the errors. Okay, it's not a universal model that works for any period of data. All right. Okay. Now in the next cell, I want to show you the 1 day ahead forecast, because in the Gold DLM project, I also used that model, the model H, to forecast the next day's price. This is the data from 2023, so we can get the ground truth quite easily. And the data is also provided in my GitHub, so that's why I just read the CSV file from that link. So I extract that ground truth and compare it with my forecast. Okay, and I also plot it. All right. Here I'm just plotting two values actually, one here and the other here. And we can see that the ground truth and the forecast go down. So even if there is a discrepancy between the ground truth and the forecast, but at least the direction is correct. I don't know about you, but I think traders would care a lot more about the directions. Yeah, anyway. For me personally, I would be happy with getting the directions correct. Alright, so that's for the high prices. Now, let's do the same for the low prices. Well, this is actually exactly the same. So, yeah, you initialize the model, and then because we only have one component, so we have only one function to build the model, and then the order is 3. Yeah, I didn't set the prior mean this time, but yeah, it's okay. So yeah, I don't think we can really compare the low prices with prices from the Gold DLM. Actually, I already tried various values, either including or excluding the parameters, and what I found is that including the mean zero, the M0 parameter, doesn't change much of the forecast and of the fitness of the model. Okay, now the sampling is done. As in with high prices, we also need to take the summary of the posterior values taken by the Gibbs sampling. And yeah, so we reapply this MCMC mean for the matrix of dV and dW, and that will be stored as posteriors, and then use these posteriors to reinitialize or rebuild the model. And yeah, this is model L now, and after rebuild the model, we put it into DLM filter. Okay, so we filter, but this time with the low prices of gold and with a new model. And then we compute the RMSE for the low price and plot it. Okay, so now the root mean squared error for the low prices is a bit higher, is a bit larger, that is 4.12, 4.12. Okay, now let's exclude the high prices and the filtered level for the high prices. If we look only like this, the low prices and the filtered level, it looks still really well. But we can see here, this is where the model doesn't match as well as in this period. Okay. Let's enlarge this. There are a bit discrepancies, but yeah, of course, this is still very, very well. Well, you know, if we do it with other model, like for example OLS, or ordinary least squares, or with machine learning, or with any other model, non-Bayesian models, we might say that this plot would indicate that our model overfits, our trained model overfits. But this is Bayesian framework, and I think the advantage of using the Bayesian framework is that this is not overfitting. Like, yeah, so the data that we receive at time t can update our beliefs and therefore inform us about what would happen at time t plus 1. So we already see with a high price as well that the 1 day ahead forecast is also very good. So I wouldn't say that it's an overfit. But of course, the big disadvantage is that DLM is only suitable for short-term forecasting. That means, yeah, it's the best for forecasting one unit time ahead. Okay, so for the last segment here, I just want to show this model performances compared to several values. So the first is the original model for the high price. Oh, by the way, this is only for the high prices. Okay, so the first is the model H from previous sampling, the Gibbs sampling model H, compared with my original model H from my DLM code project. Okay, let's see the forecast of those models. Okay, so 0.6 here is the error between the ground truth and the forecast from my original model. Alright, I'll show you the plots later. And then secondly, I want to also add the model performances from MLE. So here's the thing. The variances can be approximated by two ways. The first is this Gibbs sampling, and the second is using MLE. I've discussed this in my second video, and to apply that, I also use this dataset. So now I guess the cycle is complete. We can compare all of them. So using MLE, the approximate dV is AT, and then the approximate variance is W1 is 87, and then 90 for W2 and 86 for W3. Okay, we will see how that looks like in the forecasted values. This model is just showing the filtered level, so the fitted model. It's not showing the forecasts yet. Okay, if we just look at this without zooming in, we would think that all of the three lines almost at the same places. Okay, now let's see the forecasts. Okay, so here it is. The blue line is the ground truth. So yeah, the ground truth of the price is going down, and then except for the forecast from the model, which variances are sampled from MLE, the others are doing quite good. Like the direction is correct and the gap is not that big. But this is not for generalizing in any way that MLE is not good. MLE is worse than Gibbs sampling. It's just that for this particular project, it seems that Gibbs sampling does a better job than MLE in approximating the variances. And actually there are still many ways to explore this project, but I think we should end it here. The main focus of this project is to explore and discuss Gibbs sampling and how we can use Gibbs sampling into our real project. Like how can we use what we get from Gibbs sampling to have our model trained and eventually forecast something. So thank you so much for watching. Please consider subscribing to my channel, Timely Time Series, and I'll see you next time. Bye bye.